What's up everybody, welcome to another video, and I hope you're ready to flex those brain muscles, because in this video we're going to do a pre-calculus final exam review, and this is going to be part one of hopefully many parts. And in this video we're going to cover inverse functions, exponential functions, and log functions. So if this is stuff that you need help reviewing, then you're in the right place. Go ahead and click the description below. I made a worksheet all by myself with 9 questions covering these topics. So hopefully this will help our review. Check it out, print it out, try this on your own, then come back and watch this video to check your answers and to get help with the ones that you're stuck on, right? That's the point of this video. As I always like to say, math is not a spectator sport. You have to try it on your own in order to learn. So please don't just watch this video and copy down what I'm doing. You're not gonna learn that way. Try this on your own, then come back and check your answer, okay? So that being said, I will have timestamps below with all the questions to make it more convenient for you to go through and click on the ones you need help with. And I hope you all enjoyed this video. I hope it helps. Like, subscribe, share it with your friends. And that's it. Let's go ahead and get started. So number one gives us this rational function and tells us to find the inverse of this function and find the domain and range of both this function and its inverse. So we're going to go ahead and start with finding the inverse. And remember, to find the inverse of a function, we switch the position of x and y, and then we solve for y. That's how we find the inverse. So I'm going to switch the position of x and y. So both these x's are going to become y's, and this f of x, which kind of acts as a y, is going to become an x, right? So we have x equals 3y minus 1 over y plus 2. And now we're trying to solve for y, and you may already notice that there's 2 y's here in 2 different positions. And you may think that's going to give us problems, and it will kind of, but there's something slick that we can do. Maybe you already know what it is, but I'll show you here in a second. So I definitely want to clear the fraction. So I'm going to multiply both sides by y plus 2, because doing that will get rid of the fractions, right? So y plus 2, those are gone. And now I have x times y plus 2 equals 3y minus 1. So let's see if I have room for that step here. X times y plus 2 equals 3y minus 1. So I'm going to distribute this x, right? Distributive property, because I just want to separate out all my terms and see what I have here. Let's see. X times y plus 2 times x, and this still equals 3y minus 1. Is that right? Yep, we're caught up. And again, you see that y is in 2 different terms in this case. And whenever we have this happen, we have a variable that's in 2 different terms and we're trying to solve for it. Generally what we do is we group those terms together and we factor that variable out, right? Because if we don't do that and I just solve for this y or this y, my y is going to have a y in it, and we don't want that. We want y equals something, and we want that something to all be in terms of x, right? So we're going to group these y terms together, factor out the y, and then divide by whatever's left over. So I'm going to do 2 steps at once. I think I can handle it. I'm going to subtract 3y from both sides to get rid of this 3y and move it over here with the other y term. And I'm also going to subtract 2x to move this term that doesn't have a y in it over here with the other non-y terms, right? Minus 2x. I think I did everything I needed to do there. That gets rid of that. That gets rid of that. Am I all good? I think I am. Let's see. Let me draw this arrow, see if I can write out the next step. This is x times y minus 3 times y. And that equals negative 2x minus 1. Hopefully y'all can see to this end of the board. Now as you can see, I can factor out my y. So how I like to do this normally is I'll write y, and then I write the parentheses, and I think of, okay, how can I write this out to where it's the same as this? I know I need an x in the first term minus a 3, right? So this one's pretty straightforward. X minus 3, and that still equals, let's see, minus 2x, negative 2x minus 1. Now I really just have 1 step left, right? Y times x minus 3. How can we get rid of this multiplication division? Simply just divide by x minus 3. Divide by x minus 3. That's gone. Divide this by x minus 3. And now we have y equals this, and it's all in terms of x, so we're good. And remember what we said y was? That's our inverse function. I can just erase the y, put the f inverse notation. So instead of writing this out a second time, I'm just going to write this is our inverse function. F inverse of x equals negative 2x minus 1 over x minus 3. Now we're going to find the domain and range of both of these. I'm going to need to erase though to make a little bit of room. So to find the domain and range of a function and its inverse, it really helps to understand this relationship between functions and their inverses. And that relationship is that the domain of this function is the same as the range of its inverse. And the range of this function is the same as the domain of its inverse because all the x's and y's switch, right? Makes sense. So really what I like to do is find the domain of each function, and then that's how I get the range of the other two, right? It's just knowing these domains, because in my opinion, it's a lot easier to find domain than it is to find range. Range is a little more conceptual. Domain is pretty easy. You can probably find it by just looking at these two, right? And to find domain, we just look at a function, we think of what can't I plug into this function? What doesn't work? We know we can't have 0 in the denominator, so whatever I plug in, it can't have a 0 in the denominator. -2 makes the denominator 0, so we have to exclude -2 from the domain, but anything else works. So you can write it in several different notations. I like this interval notation from -infinity to -2, union -2 to infinity, and that's the domain of this function, right? Because we can't plug in -2 because that gives us a 0 in the denominator, and by the same logic, we can't plug in 3 to this function. Exact same logic, we just can't have 0 in the denominator. It's not allowed. And now what can I do? Well, I can copy down this range from this domain because we know that they're the same because these are inverses. And then we can copy down, we can do the other way as well. So this range goes, it just excludes -2, and then this range just excludes 3. Right, so this is the way I like to do it. You could also know a thing or two about horizontal asymptotes. If you know a thing or two, you can see that this has a horizontal asymptote at -2/1, right? You take the ratio of the coefficients. So the horizontal asymptote means that it's going to go all the way to infinity, getting closer and closer to -2, which makes sense that we're excluding -2. But I still like just finding the domain in both and then copying down the range from that as well. So hopefully that makes sense. All right, for number 2, we're going to do a similar thing. We're going to find the inverse of this function and then find the domain and range of both this function and its inverse. The only thing that's different is this is not a rational function, it's an exponential function, okay? So what we can expect is to end up with an inverse function that is a log function, and specifically natural log, because the bases will always be the same. So I just want to point that out, because if you end up with an inverse function that doesn't have natural log in it, go back, retrace your steps, see where you messed up, right? So we know what to expect from this. So let's go ahead and start. We can replace our y with x, and we can replace our x with y minus 1 up there in the exponent. And what I really want is to get e to the something, right? Equals something. And the reason why I want that is because we have our y that we're trying to solve for, and it's in the exponent. And how we bring it down from the exponent is using natural log. We're going to take the natural log of both sides. But before we do that, we really want to isolate this e to the something, right? It's really what we want to do. So we can subtract 1 from both sides, right? And what that'll give us is, let's see, x minus 1 equals -2 e to the y minus 1. And then what we can do is divide both sides by -2. Divide. These are gone. Now what we really have is, let's see, e to the y minus 1, that equals this. Let me recopy this down and clean it up a little bit. All right, equals e to the y minus 1. So this is the step where we use the natural log. We have e to the something. Now we can ln, we'll use a different color here, ln of this whole thing. And we do that on both sides, ln of this whole thing. And we have a law that has to do with logarithms, where if we have ln of something to some power, we can bring that power to the front as a factor, right? And ln of e, the bases are the same, so that's just 1, so those are gone. So that's why we pick ln. That's why we take the ln of both sides, because not only does it bring the exponent down, but it completely gets rid of the e. So now what we're left with is y minus 1. And if you need that expanded or elaborated, go check out my video on that. Equals ln of x minus 1. It's okay that we have this ugly thing in the natural log. It's okay. And then let's see what we're doing here. Add 1 to both sides. Y equals ln of x minus 1 over -2. And always use your parentheses around ln. A lot of kids in my class were not putting parentheses around logs and ln's. Always do it. It keeps you more organized. Because once you have ln of something, you don't want to change that inside stuff. Like if you add 1 to both sides, it has to stay outside the ln. And this is, in fact, our inverse function. Let's replace this with f inverse. Use the right notation. And that's it. Now let's find the domain and range of both of these. So to find the domain and range, I'm going to do a very similar thing that I did in the first problem, which is just I'm going to find the domain of both these functions and then copy down the ranges, because I know the range of the inverse is the same as the domain of the original function and vice versa. So what's the domain of this original function? Well, the domain of pretty much any exponential function is all real numbers, right? We don't have any square roots or denominators that can be 0. So we go from negative infinity to infinity with this domain, which means that this range is also negative infinity to infinity, right? So now what about the domain of our inverse function? What can't we plug in to this? Well, we can't have what inside of logs? We can't have negatives or 0. So this entire argument has to be greater than 0. So that's what I do, is I just take the entire argument, whatever's inside the log, and I set it greater than 0, and I solve this inequality. So I can multiply both sides by -2. -2 times 0 is still just 0, but we got to be careful, because multiplying both sides by a negative flips that inequality, right? So be careful, a little bit tricky with that one. And again, you could have also looked at it, and then I added 1 to both sides. You could have also maybe looked at it and been able to tell that it's less than 1, but this always works as well. So the domain of our inverse, let's see, less than 1. We got to be careful with our interval here. That means we're going from negative infinity up to 1. And that means the range of our original function is from negative infinity to 1. And this should line up if you know anything about transformations, because this negative, it's reflecting. We know that it's decreasing, right? So hopefully this makes sense. So now we're going to find the inverse of this log function, as well as the domain and range of this function and the inverse. Hopefully this is feeling a little bit familiar by now. Hopefully that you're feeling good about this. Really, it's all the same process. Switch the x and the y, solve for y, right? So the equation may look different, but same process. And what can we expect our inverse function to look like? We have a log, so we can expect it to be an exponential function, right? So hopefully that's making sense too, specifically with base 10. There's a little invisible 10, right? When there's no written base on a log, that means it's base 10. So we can expect our inverse function to be 10 to the something that looks kind of like that. So I think it's helpful to notice that. I don't know. Here, we'll replace our y with an x and replace our x with a y. And this is what we get. Now I want to solve for that y. So we do the same thing with logs and exponentials to solve for stuff that's in them. We just want to isolate this log. We want to get log of something equals something so that we can raise both sides from a base of 10. Right? With our exponential, we want to get e to the something equals something so we can take the natural log of both sides. But same idea with both. We want to isolate this log of something. So I need to add 1 to both sides. And I have x plus 1 equals 3 times log y plus 3. And now I can divide both sides by 3. Divide both sides by 3. That will cancel this 3. I'll draw a little arrow here to my next step. I have x plus 1 over 3 equals log y plus 3. Now I have it exactly where I want it. Log of something equals something. Now I can erase both sides from a base of 10. I'll use a different color here. And there's a couple different ways this is taught. You can do it this way, where you raise both sides from a base of 10. Or you can think of it using this little trick where you draw a 10 here and you draw the arrows and you rewrite it as an exponential equation. Either way, you'll get the same thing. Either way, you'll get this canceling. You'll get y plus 3 equals 10 to the x plus 1 over 3. So it looks a little ugly. That's okay. Hopefully y'all can see that. 10 to the x, I'll put parentheses 2. 10 to the x plus 1 over 3. All I gotta do is subtract 3 from both sides. Subtract 3, now I have y equals, subtract 3, and remember, y equals this, that means this is our inverse function, because whenever we get y equals something, we just replace the y with that f inverse notation. So this right here is our inverse function, 10 to the x plus 1 over 3 minus 3. Now let's find the domain and range of both these guys. So to find the domain and range of both of these, we're just going to do the same thing that we've been doing, which is find the domain of both, and then that's how we're going to get the range of both, because we know that the range of our original function is the domain of our inverse function and vice versa. Hopefully y'all are catching on to this by now. So let's find the domain of each function. What about this first one, the original function? Well, we know that whatever's inside the log has to be greater than 0. So I can just solve this simple inequality, and I get x is greater than -3 just by subtracting 3 from both sides. So that's the domain of this function, from -3 to infinity. Pretty easy, right? Which means that's the range, which means we're halfway through already. Now, what's the domain of this inverse function? We have an exponential function, no zeros in the denominator, no square roots, nothing like that. Any real number I can plug into this. There's no issues, right? Negative infinity, which is true for almost all exponential functions. Occasionally you see a weird example, but you can pretty much always put all real numbers. That's it. All right, so number 4, we're solving a couple of exponential equations. And with these exponential equations, we have 2 main types that we see in precalculus. One type is where we can get the same base on both sides, and then we can just solve for the exponents, right? So we can set up the same base on both sides, which actually is what we can do in this example. The other type, we can't do that. We have to log or natural log both sides, and our answer is going to be kind of messy, a bunch of, log stuff in our answer. So keep that in mind that we have those 2 types, and really be looking out for your factors of 2 and 3. That's what you see most common. So if you see like a 2 and a 16, or a 3 and a 27, stuff like that, then you can write them in the same base like we're about to do with this question. Just keep that in mind. So 4 is 2 squared. So I can rewrite this as 2 squared to the x squared power equals 2 to the x. So now what I can do is use my exponent laws. I can say, well, a power to a power, I multiply 2 times x squared. So this is the same thing as 2 to the 2x squared power. And why do I care so much about these same bases? Well, what I can do here is I can say we have 2 to some power equals 2 to some power. The only way for this to be true is for these powers to be equal. So we can just disregard the bases and solve this simple quadratic equation, 2x squared equals x. So now we have a simple equation. We can subtract x from both sides, get 0 on one side. Now we can factor. We'll factor out an x. And now we use the 0 product property, I think it's called, right? 2 things being multiplied together to equal 0. That means either x is 0 or 2x minus 1 is 0. And if you solve both those equations, you get x equals 0, x equals 1/2. I'll trust that you can solve both those equations. These are the answers you get, and those are the 2 solutions to this exponential equation. All right, so 4b, we're solving another exponential equation, but this time we can't get the same base on both sides. So what we have to do is use either log or natural log so we can get this exponent down and solve for x. I'm going to use natural log because it's 2 letters instead of 3, and I'm really lazy, so ln, both sides. And again, the reason why we need log or natural log is because what we're trying to solve for is in the exponents, and our properties of logarithms say that we can bring down this exponent in front as a factor. That's why we need it. Hopefully that's making sense. So what we have here is x plus 2. We can bring that out in front times ln3, and this equals x times ln2. And maybe you're already noticing that we have x in 2 positions, and we're trying to solve for that. It's feeling hopefully familiar by now, kind of like number 1 when we found the inverse of that rational function. So we're going to end up having to group these x terms together and factor out the x, right? Hopefully you're getting comfortable with that idea. So let me distribute this ln3. I have x times ln3, and the reason I write the x out in front is because if I put it after, I'd have to put parentheses around the ln3 to specify that it's not ln of 3x, it's ln3 times x, right? So I just always write it in front, but just to be clear there, ln3, that equals x ln2. So again, I need to group these x terms together. I'm probably just going to bring this to the other side. So I'm going to do that all in one step right now. I think I can handle it. 2 steps at once. So I'm subtracting x ln2 from both sides because I want to bring those x terms together. That's going to get rid of this, but I also want to subtract 2 ln3. And again, do this one step at a time if you're not super comfortable with this. These are gone. These are gone. So I have negative 2 ln3 on this right-hand side. And on this left-hand side, I have both my x terms just like I wanted. So x natural log of 3 minus x natural log of 2. And that equals negative 2 natural log of 3. All right, now let's factor out the x. So I like to write the x and then write my parentheses and see what else I need. ln3 minus ln2, right? And then you can double check if you want, distribute it back out. We get right back to there. We're good to go. this equals negative 2 natural log of 3. So now we have x times something equals something. We can just divide, right? Divide both sides by ln3 minus ln2. That's still just a number, even though it looks long and intimidating. We can still just divide by the whole thing. So if we divide by ln3 minus ln2, right? These guys both go. We have x equals negative 2 ln3 over natural log of 3 minus natural log of 2, and this is our final solution for x. This equals x. That's what we wanted. You can leave it in this form. That's fine. You don't need to punch this in a calculator, at least for my class. You don't. I wouldn't expect you to. I guess check with your professor, but this is a good answer. All right, so for number 5, we're really just practicing using our properties of logarithms to expand this into as many terms as we can and make sure we write all of our exponents out in front as factors. So pretty straightforward. I like to start with the division. The division we can separate and it becomes subtraction, and we know later the multiplication can become addition, all right? So as long as you know these log properties, this shouldn't be too bad. So I'm gonna separate first the division. So we have log of x times x plus 2 minus log x plus 4, and this is squared. And what can we do with that squared? In our next step, we can bring it out in front. We can bring it out in front, okay? And this we can go ahead and separate with addition, and then I think we're actually done. So what do we have here? Log x plus log x plus 2 minus 2 log x plus 4. So now we have expanded this as much as we can. We make sure to write all of our powers, all of our exponents as factors, and I think we're good to go. So hopefully that makes sense. So our last example, we took a single log expression, we fully expanded it. We wrote all the powers out in front as factors. Now we're gonna do the opposite. We're gonna fully condense this log expression and write all our factors as powers. So really what we're doing with these examples is just practicing using the properties of logarithms and making sure you know how to use them to go back and forth, right? It's really that simple. So what we're gonna do here is fully condense this, combine this into one log expression. First thing I really need to do is move this 2 up front as an exponent. Remember, that's the last thing we did in our last example. Well, that's the first thing we do here because we're going the opposite direction. That's how I remember it, at least. So we're gonna bring this 2 out in front. So what I have here is log base 2 x plus 1 squared minus log base 2 of x plus 3. I'm just copying the rest down. And our next step, you know that this subtraction is gonna become what? Division, right? It's gonna become division, and they're both being subtracted, so they're both gonna end up being divided, and that's really what's gonna happen. And I'll just go ahead and give you a pro tip. Subtraction, write it in the denominator. Addition, write it in the numerator. It's that simple. You can go step by step, and I do have a video on this where I go really step by step and break it all down. But in general, that's what I remember. Subtraction, put it in the denominator. Addition, put it in the numerator. So what this is gonna end up being is log base 2. And it's gonna be x plus 1 squared in the numerator. And in the denominator, I'm gonna have x plus 3 because there's subtraction there, and x minus 1 because of that subtraction there. And it's really that simple. But again, if you want a full detailed description broken down, check out my other video. Maybe I'll put a link right up there. All right, now for number 7, we're gonna solve some log equations. There are 2 different things you really want to get out of these log equations. Either log of something equals log of something, or log of something equals some number. If we can get either of those things, then we can solve the equation really easily. In this case, we don't have either of those things. We don't have log of something equals log of something, and this 2 is messing us up from getting that, right? And we don't have log of something equals some number yet. We don't have that yet, right? But we can get that using our properties of logarithms. This addition we can combine as multiplication, then we can say log of something equals some number. So hopefully that helps. Just some general tips with solving these log equations. You want to get one of those 2 things. So we can combine these because we know that our properties of logs, this addition can become multiplication. And now we can just multiply this out. Now we do have log of something equals some number. This is log of x squared plus 15x equals 2. And you can do a couple different things from here. Raise both sides from a base of 10, or use this little trick with the arrows that I like to do. 10 to the 2nd power equals all this stuff, right? Whatever way you do it, as long as you get to x squared plus 15x equals 100. As long as you get to that, whichever way gets you there. Now I'm going to get 0 on one side and factor and solve, right? This is a quadratic equation. Pretty straightforward algebra from here. So x squared plus 15x minus 100 equals 0. What does this factor to? Two numbers that multiply together to be 100 and add together to be 15. There's quite a few factors of 100, but let's see. Plus 20, plus 20 minus 5. Yeah, that works, sorry. Plus 20, and maybe it would have took you a little bit longer, that's okay. X minus 5. And now I just solve each one of these. So I have two solutions, x equals negative 20, or x equals 5, or do I? But wait, remember what we have to do with these log equations? We have to go back and double check our answer, especially when we have these quadratics that we end up with. Go back, double check, make sure you don't create any zeros or negatives inside either of these logs. This negative 20, this is bad news, right? I can't plug these into either of those logarithms. I have to throw that answer out, so I actually just have one solution, x equals 5. So be careful. Whenever you get these quadratics from these log equations, go back, double check your answers, because you'll almost always have to throw one of them out. But hopefully that makes sense. All right, here's 7b. We're solving another log equation, and this one's actually a lot easier than the last one. So maybe I should have done them in the opposite order. Sorry about that. But we already have log of something equals some number. This is pretty much what we want, right? So we can use this little arrow trick that I like. You can raise both sides from a base of 2. You'll get the same thing either way. You'll get 2 to the third, which is 8, equals x squared plus 7. You should get to that, right? Now what do? Well, subtract 8 from both sides, right? Quadratic, get 0 on one side. So we have x squared minus 1 equals 0. We can factor this into x minus 1, x plus 1. And that means our two solutions are x equals 1 and x equals negative 1. And you could have, I guess, let's see, subtracted 7 and square rooted both sides, but don't forget to plus or minus. That's a very common mistake. That's why I prefer this way, because you don't make that mistake. But if you do that, plus or minus when you square root both sides. So plus 1, minus 1, your two answers. We can go back and check these. They're actually both good. They both get squared. So any number, I think, really works for this one. Since it ends up getting squared, it'll be positive. Those are our two solutions. All right, so number 8, both parts A and B involve graphing, which I know is everybody's favorite thing to do, right? But in all seriousness, this is probably the tougher part of this review, in my opinion. So hopefully I can give some suggestions and give a little tips that will help you graph something like this if this does come up on your exam. So for me, what I think really helps with this kind of graphing stuff is knowing just what a basic exponential function looks like, right? Like if I give you something like this, knowing a little bit about this, like knowing that the domain goes from 0 to infinity and knowing that there's a horizontal asymptote at the line y equals 0, right, at the x-axis. Knowing just those two things really helps. A lot of students, they don't know that, and it makes it really hard to apply these transformations, to make these changes if you don't even know what this looks like, right? So I really highly recommend get familiar with this, and the same with the basic log function as well, like just log x, what does that look like, right? And kind of get familiar with that, and then it'll make this stuff easier. So we can use these transformations to gather some information, but I typically don't fully rely on the transformations to sketch the entire graph. And I'll show you what I mean. I definitely use this vertical shift because what this tells me is how the asymptote is changing, right? Because the only way for a horizontal asymptote to change is if we shift up or down. So we're shifting down 2 units. So that means down here at negative 2. I'm going to use a dotted line. That's our new horizontal asymptote. This reflection, this is really important because what this tells us is that as our x values get bigger and bigger, our y values head toward negative infinity, which means we're going to be hanging out down in this area, right? So that's really important. But what we can do from here, what I like to do is make a little table. And I like to plot a couple of points. Get a couple points, that's a y, by the way. But I want to strategically pick these x values so that they're really easy to evaluate. I don't want to have to use a calculator, right? So I usually pick the x value that makes this exponent 0, which in this case is 1, and the x value that makes this exponent 1, which in this case is 2, okay? If I can get these two values, they're really easy to evaluate and it'll help me draw this graph a lot. So when I plug 1 into this function, I get 1 minus 1, that's 0. 3 to the 0 power, that's 1. So we have a negative 1, right? This negative is chilling out in front. Negative 1 minus 2, negative 3. So when I plug in 1 to this function, I get negative 3. When I plug in 2, I get 2 minus 1, that's 1. 3 to the first power, right? That just becomes a negative 3. Minus 2, that's negative 5. If I went too fast, go back, pause the video. make sure this checks out. But now we have 2 points. This is really good for us because we can plot these 2 points, 1 and 2. So here at 1, we're at -3, and at 2, we're at -5. So -3 here, -5 here. It looks something like this. This is, again, a rough sketch. And we know that as we head toward negative infinity, we head toward this horizontal asymptote. So this is a pretty good sketch of our graph, right? And if you wanted to get more points, you could get those. You could plug in 0, find out exactly what that point is. You can plug in other points if you want to get more accurate, more specific. But I think this is a pretty good sketch. So I've used a little bit of these transformations to get at least what the asymptote was and the domain and that sort of thing. And then I plotted some points to be a little more specific. But hopefully this helps. So hopefully what we've learned from that last example is that it really helps when we're graphing these log and exponential functions to have some idea of what the parent function looks like, as well as the domain, range, asymptotes, that kind of thing. So I highly recommend, if you don't know anything about this function, go back and review. Same with the exponential functions. Learn about these basic functions, and then you can pretty easily apply these transformations and graph these more complicated functions. So we're going to do the same thing as last time. We're going to compare this function to its parent function, see what information we can gather, and then plot a couple of points and sketch the graph. That simple. So we know that these log functions, instead of a horizontal asymptote like the exponential functions have, these have vertical asymptotes at the line x equals 0. So vertical asymptotes, how can those change? From horizontal shifts, right? Whereas we had the exponential functions, they have horizontal asymptotes, those change by vertical shifts. So we're kind of seeing the pattern here. So we can look at the horizontal shift and we can see that our new vertical asymptote is going to be shifted left. Okay, so our new vertical asymptote is here at x equals -1. That's our new vertical asymptote. What other information can we gather? Well, we don't have any reflection, so we're going to be doing something like this, going up this way. But let's find some points. And I like to find the points that make the inside of this log not 0 and 1 like we did with the exponential, because 0 isn't even defined in here anyway, but 1 and 2. And I'll show you exactly why I picked those points. So what makes this whole argument 1 and 2? Well, that's plugging in 0 and 1. So when x equals 0, we have 1 in this argument. When x equals 1, we have 2. And the reason why I picked those values is to make it really easy on myself, because if we have the log of 1, we know that that's always going to equal what? Well, that's like saying 2 to what power equals 1? That's 0, right? So if we log base 2 of 1, that's going to be 0. This whole thing's going to go, and then we can see that we're left with a 2 out here. So 0, 2 is 1 point. Really easy to find that, right? And when we have log base 2 of 2, we know that that's just 1. Those can cancel, right? That's how we were solving those equations and that sort of thing. So log base 2 of 2. So I picked the number 2 to be in here because that was the base. If it was base 10, I would have plugged in 9 because I want that to be the same, because I know that's going to be an easy thing to do, right? Hopefully that's making sense. So I plugged in 1, I get 2, log base 2 of 2, that's just 1. 2 plus 2, that's 4. And if I went too fast, pause, go back, slow it down if you need to, try this on your own. All right, so I have 2 points here, which is pretty good. 0, 2. 1, 2, go up here, and then 1, 4. So I'm right about here, and then I have up here. And this is a decent sketch. I mean, I kind of knew where the graph was going to be going. And again, if you want to find that, let's see, it would be an x-intercept, you can go and find that. You can set this whole thing equal to 0 and solve that if you really want to. It just depends how specific you're trying to be. But if they use the word sketch a graph, I think 2 points is enough, and just like the general, you know what I mean, the general sketch of the graph. So hopefully this makes sense. Hopefully you like my method of combining these transformations and using a little table. Hopefully this helps you on your exam. All right, so for number 9, we are given this function that represents the number of bacteria present in a culture at a time of t, and this time is in hours, and we're asked to do a few things. I'm just going to run through all of these all at once. So first, we're asked to determine the initial amount of bacteria. So initial amount is when time equals 0, right? Pretty straightforward. When time is 0, that's the initial amount. So we can literally just plug 0 in for t. So when I plug 0 in for t, I get 0.01 times 0. That's just 0, right? Anything times 0 is 0. So that's 0. E to the 0, well, that's 1. Anything to the 0 power is 1. So I have 1 times 1,000. So for part A, my initial amount, it's just 1,000. And what can we notice? Can we get a pattern from this? Well, yeah, it's always going to be this number being multiplied out in front. That's always going to be our initial amount, because whenever we plug in 0, this is all going to become 0 up here, which means this is going to become 1, no matter what that is. which means they're always just left with that number out in front. So just a general tip. But if you don't believe me, just plug in 0 for t every time. So part B says what? What is the growth rate? So the growth rate is actually always this number up here multiplied by the t. Usually the formula is like p times e to the rt, where r is the rate, p is the initial value, right? So the growth rate is 0.01. And you just get that by knowing the form of this exponential growth function. Part C, what is the population after 5 days? So we're looking to plug in a time and get out a population, because remember, this function represents population at a time of t. So we're looking to plug in for t. So we're looking to evaluate this, 1,000 times e to the 0.01. Are we plugging 5 into here? No, right? Be careful with the units. 5 days, our time is in hours. So how many hours are in 5 days? 24 times 5, 120. So 0.01 times 120. And you can literally just plug this whole thing into a calculator, right? That's actually the only way to get this. Of course, you can't really do this in your head or by hand or anything like that. So if you plug this all in your calculator, you get 3,320. And I think I rounded to the hundredths place because I got 0.17. That's what I wrote down. So that's part C. You're literally just plugging in a time, making sure your units are correct, and then just plugging that in a calculator. It's that simple. For part D, we're going the opposite way. Now we're asked to find a population. How long will it take for the population to double? So remember, the initial amount was 1,000. That means that's the initial population when time is 0, right? So the population is 1,000 when our time is 0. We're looking for that to double, right? So we want to set 2,000 equal to 1,000 e to the 0.01 t. And now we want to solve for t, right? So now we have this exponential equation that we're solving for, kind of like we did in the earlier example. So I can divide both sides by 1,000 and then take the natural log of both sides. When I divide by 1,000, I get rid of this 1,000. I'm just left with e to the 0.01 t on this right-hand side. This left-hand side actually becomes 2. 2,000 divided by 1,000, that's 2. So I have 2 equals e to the 0.01 t. E to the 0.01 t, sorry about that. And now when I take the natural log of both sides, let's see if I ln both sides, ln, the exponent comes out in front. Remember how this works? Exponent comes out in front. The ln of e, that's just 1. So what we're left with is ln of 2 equals 0.01 t. So to solve for this time, I simply just divide both sides by 0.01. So 0.01, which I'll again need a calculator, or pretty much always need a calculator for these exponential growth type problems. So for these, you will need a calculator. If you punch this in a calculator, you should get 69.314. I took this one to 3 decimal places for some reason. And I'm running out of room, I'll write it up here, 69.314. And remember, that's in hours, so like almost 3 days, because 3 days I think is 72 hours that it takes for this population to double. Okay, so we need to know how to go both ways. We need to know how to plug in for time to get the population and plug in for population to get the time. It's pretty straightforward though. I think the earlier examples, if you have those solving exponentials down, the equations, then you'll be able to do this pretty easily. All right guys, so that's it for part 1. Make sure to stay tuned for part 2. If you have any feedback for me, let me know in the comments below. Make sure to like the video, subscribe, share this with a friend who you feel like this video could maybe help. But most importantly, keep flexing those brain muscles. I'll see y'all later.